Hey guys, welcome. Yeah, so if you haven't already watched the introduction video and multiplication video on complex numbers and polar coordinates, then you should watch those videos first. That's unless you are familiar with what's discussed in those videos, and I'll link those videos below this one. Anyway, yeah, if you know the basics and how to multiply complex numbers and polar coordinates, then you are ready for this video, which is a discussion of Demoivre's theorem. What we're going to do is prove Demoivre's theorem and then give a hard but interesting example. So the example I offer in this video is not really like your first example on Demoivre's theorem, like because it's a bit too hard for a first example, but it's a very fun example. All right. Let's get started. Now, from the intro video, we know that a complex number is z written in rectangular form or Cartesian form is x plus I times y, can be written in polar form like this. And what Demoivre's theorem tells us is that if we take this polar form of our complex number and we want to raise z to some power n, it doesn't matter how big the power n is, then this is the result. So this is what Demoivre's theorem states, which is that z to the n is this. And that's what we're going to prove in this video. Now, in the intro video, we came up with an abbreviation for z equals r cosine theta plus I times r sine theta, and that was r cis theta. So using that abbreviation, z to the n can be written like that. R to the n cis n theta. That's to say that this right-hand side here is the same as this right-hand side here. Yeah? Okay, cool. Now, proving Demoivre's theorem is actually pretty simple if we know how to multiply two complex numbers in polar form. So this is what we do. So z is written in polar form, and again, it's abbreviated version of the polar form is like that, r cis theta. And so what would z squared look like? It'd be z times z, and so in the abbreviated form, that'd be r cis theta times r cis theta. And so r times r is going to make r squared. Otherwise, we know that multiplying two complex numbers will require that we multiply the moduli, so r times r, and then add the arguments, which is add the thetas. So theta plus theta makes 2 theta, right? So the result of z squared is r squared cis 2 theta. If you need to see the details of this, watch the video on multiplying complex numbers in polar coordinates or in polar form. Yeah? Okay, cool. But yeah, this is how we could very efficiently multiply z by itself, which is this result. And that's really the advantage of working with complex numbers and polar coordinates, which is they make multiplication and division very easy. And they give us an insight to like what complex multiplication and division are about, which is about rotation. Okay, anyway, what would z cubed look like? Well, it's r cis theta times r cis theta times r cis theta. And so we multiply the 3 moduli, that's r times r, and r cubed. And we add the 3 arguments, theta plus theta is 3 theta. So we get r cubed cis 3 theta. All right. So then if we move by analogy, then it's clear that z to the n would be multiplying n r cis thetas. So it'd be r cis theta times r cis theta n times. So that's multiplying n r's, and that's r to the n, and then adding n thetas, that's n theta, right? Okay, there it is. That's the proof. And now we are ready to move on to the example. So here's the example. The example is, as I said, a very interesting but pretty challenging question, which is for this particular z right here, negative root 2 plus I times root 6, we need to figure out when z to the n will be strictly a real number. That is, we need to figure out for what values of n raising z to a power n will have us like basically get rid of the imaginary part. And then part B, that's part A. And then part B is we need to figure out what powers of z will make z an integer, right? So first we need to figure out how to make z strictly a real number, get rid of its imaginary part by raising it to a power, that is. And then next we need to figure out how to make z just an integer. Well, let's see. To get insight into answering these two questions, we need to convert z into polar coordinates, because this here is in rectangular coordinates. First, notice that root 6 can be written as root 2 times root 3, and that's pretty revealing because as soon as we plot z, we see that the triangle we're working with as a reference triangle right here is a 30, 60, 90, and that's because we've got x and then x root 2 right here, and we know that the hypotenuse is supposed to be 2x, and so that's 2 root 2, or root 8 is going to be the magnitude of z, that's r, right, in polar coordinates, right? R is going to be 2 root 2 or root 8. But again, the fact that I wrote root 6 is root 2 root 3 allowed me to see that this triangle here is a 30, 60, 90 degree triangle, where this reference angle is 60, and therefore theta is actually 120, right? Theta, remember, is measured from the positive real axis. So yeah, keep that in mind. But yeah, cool. So we're just right now working on getting z in polar form, and so here it is. And the abbreviated version, z in polar form, is root 8, which is same as 2 root 2, and then cis 120. And so if we write it in its longer form, this here would be root 8 cosine 120 plus I times root 8 sine 120. Now, we know what z to the n is going to look like. It's going to be root 8 to the n, and then cosine n times 120 plus root 8 to the n, and then sine of n times 120. So we know like what the result should be when we raise z to an n power, where n is again an integer. And what we need to figure out is like how we could choose n so that this part, the imaginary part, is 0. Now recall that sine of an angle is equal to 0 when that angle is 180, 360, and so on. And the way z to the n works out, we multiply 120 by n, right? And so we can't really multiply 120 by an integer n and make 180, but we can multiply 120 by an integer n and make 360. That way, sine of 360 will be written here, and it will be 0. Because sine of 360, like sine of 180, is 0. What I'm saying is there's no integer n that we can multiply 120 by to get 180, but there is an integer n that we can multiply 120 by to get 360, and that's 3. And so then z cubed will do the trick of making z strictly real. Z cubed will be strictly real. And that's because z cubed will mean root 8 to the third, or root 8 cubed, cosine 3 times 120 plus I times root 8 to the third, sine of 3 times 120. So in this part, we're going to get sine of 360, which is beautiful because sine of 360 from this note on the left is 0. So we're going to get I times root 8 cubed times 0. So the I part, the imaginary part, is going to be 0. And that's what we wanted to keep z real. Notice that it's not just 3, but any multiple of 3 will make z to the n a strictly real number. So if we choose n to be any multiple of 3, like 6 or 9 or whatever, then z to the n will continue to be a real number whenever n is a multiple of 3. And so then we already know that to make z to the n an integer, we need to first make it real, and therefore we need to pick n to be a multiple of 3, and then find the smallest multiple of 3 that will not just keep z to the n real, but it will make it an integer. All right, and so the next guy that we know we have to test for n is 6, and that'll do the trick. First of all, I didn't wrap up what z cubed is and show that it's strictly real, and it is strictly real. It's root 8 cubed, right? But yeah, z to the 6 from what I just said is going to be strictly real, but it's going to do us one better, right? First of all, z to the 6 will have us write sine of 720, and sine of 720, just like sine of 360, is 0, and that's why the imaginary part will be gone, in case you weren't convinced that every multiple of 3 will keep us real for n, a multiple of 3, that is. But yeah, this 6 will also make us an integer, because z to the 6 would be like, and this should be root 8 to the 6, my bad, y'all. I'm not going to re-record this video. I forgot my square root sign in this part, right? So I need square root of 8 right here. Jesus Christ, really? Like, you're gonna make me record? No, I'll use a ruler if I have to make the square root sign. But yeah, you should be able to see very easily why this works, right? So this is root 8, root 8 to the 6, right? Root 8 to the 6 cosine 720, as I said, the sine 720 is 0, right? But root 8 to the 6 is the same as root 8 squared and then that cubed. But root 8 squared is just 8, and so root 8 to the 6 turns out to be 8 cubed. And cosine of 720 is, cosine of 720, what's that? Is 1, just like cosine of 360. So yeah, z to the 6 is going to be 8 cubed, an integer. Yeah, okay, cool. All right, I hope you enjoyed this, and keep watching lots more videos on complex numbers to come. All right, take care.